In this video, we're going to talk about ketone bodies. And I want you to, by the end of this, I want you to be able to figure out, okay, what is the problem that ketone bodies solve? What cofactor do ketone bodies allow to be recycled? What molecules are considered ketone bodies? How do liver cells react to starvation? How do liver cells react to diabetes? And finally, what is ketoacidosis? Now, what we have to do, what the ketone bodies, the problem that ketone bodies solves has to do with situations in which the body has a low concentration of blood glucose. Okay, so let's think about this. What happens when there is low glucose levels? We have to look at hepatocytes. We have to look at liver cells because these are the important cells that are necessary for regulating blood glucose levels. And when it detects that there is a low blood glucose level, it realizes, the hepatocytes here realize, uh-oh, we need to start exporting glucose to the brain. Okay, so it means it needs to start making glucose. Well, how do you make glucose? You make it via gluconeogenesis. What's the product, or what is the main reactant? Well, pyruvate turning into oxaloacetate here in the matrix. So when there isn't enough glucose within the blood, the liver cells are going to start pulling intermediates of the citric acid cycle out, turning them into glucose via the gluconeogenesis, exporting that out for the brain and other tissues. Now, here's the problem. When you do that, you begin to reduce the capacity of the citric acid cycle because you are, of course, reducing these intermediates by pulling them out to make glucose from them. So what that means is acetyl-CoA, right? That's necessary. When you make acetyl-CoA, you're using CoA molecules to make acetyl-CoA. So acetyl-CoA isn't able to go through the citric acid cycle at quick enough rates to release the CoA, the coenzyme A molecules. And that's important that acetyl-CoA be consumed in the citric acid cycle to release that CoA, because we need CoA molecules for beta oxidation, for breaking down those fatty acids. And so what happens is if we start removing intermediates of the citric acid cycle to make glucose, we are reducing the capacity of the citric acid cycle, and therefore we are reducing the ability of acetyl-CoA to give up its CoA molecule. We are therefore running out of CoA, and we are then therefore reducing our ability to perform beta oxidation. Okay, so this is the problem that ketone bodies solves. With a diminished citric acid cycle, how to resupply the CoA molecules? And the answer is this. What we do in these situations where we're starting to get to a diminished citric acid cycle is now those acetyl-CoAs, two of them combine into one another, releasing their CoA for fatty acids to use, and thus becoming these ketone bodies, these molecules that can then be shipped to other tissues and remade into acetyl-CoA and then used as energy. So let's take a look at this reaction, this ketone body formation. How is ketone body formation releasing CoA? And the answer is this. Now, these are complex reactions, and you don't need to know the details, but I do want you to know what I have sitting here on this slide. In that, the formation of ketone bodies involves two acetyl-CoAs that then get combined into an acidoacetate. So that's two carbons, two carbon molecules become one 4-carbon molecule. And then the two CoAs here then are released that can be used for beta oxidation. Now, Acetoacetate is in equilibrium with another molecule called beta-hydroxybutyrate, and both of them are considered to be ketone bodies. One byproduct here is that sometimes acetoacetate spontaneously breaks down into carbon dioxide and acetone. This is an unintended reaction, but we will get to the significance of that in a second. The important part is these two molecules, acetoacetate and beta-hydroxybutyrate, are 4 carbon molecules that can be shipped through the blood to various tissues that can then take it and convert it back into 2-acetyl-CoAs and then use those in the citric acid cycle of their cells, of their mitochondria, to get energy. But ultimately, the purpose of this here is to resupply, free up CoA coenzymes that can be used for beta oxidation. Now, let's come back to this acetone, this unintended byproduct of ketone body formation. And let's talk about uncontrolled diabetes. Let's talk about starving. Let's talk about people who are on some pretty serious keto diets. And what all of these people have in common are potentially very low blood glucose levels. Or in the case of diabetes, the liver cell thinks that the blood has a very low glucose content, right? It's tricked into thinking that because of the diabetes. Now, because of that, what happens here is that glucose uptake by the liver cells, right? It can't take up. There is no glucose to take up, or in the case of diabetes, it doesn't think there's any glucose to take up, which means that gluconeogenesis is going to increase, right? Which means that we are going to start pulling oxaloacetate out of the citric acid cycle. The cell, since it doesn't have glucose, needs another source of energy. What is that? Beta oxidation. So beta oxidation ramps up. Which means, since we are sort of stalling out acetyl-CoA use, we need to free up those CoAs, so we start ramping up ketone bodies. And if this condition persists too long, if your diabetes is not under control, if you go too long for fasting and your blood glucose level stays too low for too long, if you allow these ketone bodies to increase in production for too long, what you're going to end up with is, number one, that unintended reaction, that formation of acetone, you'll be able to smell on people's breath as sort of almost a nail polish, fruity smell. In addition, these ketone bodies will accumulate in the urine. That's called ketosis. And the ketone bodies accumulate in the blood. That decreases the pH of the blood. That's called acidosis. And this could be potentially fatal. All right, so again, please watch this video several times and make sure that you can address each one of these questions.